So today we're very happy to welcome our own Kevin Carlson, who will be telling us about free cocompletion. Thanks, Kevin.
Thanks, Evan. Thanks, Sophie. Hi, guys. So this is pretty much expository talk. Feel free to try to push me in any direction that sounds interesting. This came out of a sort of progression of synchronicities where everybody this whole year seems to be talking about free cocompletions in one or more senses. And I've kept trying to find something to grab onto in all of this, and just a couple weeks ago found something that seems like a nice centerpiece enough to justify this talk. So let's see what I've got. So if C is some kind of a thing, probably a category, but not necessarily, in some kind of context where colimits are a thing, if I fix some colimit notion, and I'll say a few examples in just a second, like all small colimits in a category or all coproducts in a double category. A free cocompletion it's going to be something like this. A morphism into something bigger. Where C bar has whatever kind of colimits I'm currently thinking about. And I is the initial such situation. So if you have any morphism into some other guy with the colimits I'm thinking about right now, then there's a unique extension to a functor on all of C bar, preserving the colimits I'm thinking about right now. Such that the triangle commutes. And I will try to, I think, write compositions in diagrammatic order today. I then F bar is F. Close paren. Some people might be about to complain about exists unique equals.
I was about to ask that question. Sorry.
Yeah, but today I get to say that and not be lying. So I'll just say it in the nicer way. There's something about like, oh, it should be unique up to isomorphism maybe, but actually that's one of the key points I want to make today is how to make it be actually unique up to equality. Any other questions or clarifications? Yeah, the next thing I'm going to write is example. OK, so maybe the most familiar to the largest number of people in here, maybe, or at least the simplest familiar one, is for C a category, fam of C is the free completion of C under coproducts. Or, according to Patterson 2024, double category. And there's a couple different notions of double categorical products and coproducts, and that's interesting. So sub-example, that many of us know and love poly is the free cocompletion of the opposite of the category of sets under coproducts. And a lot of its marvelous properties, as far as how easy it is to compute things in poly, have to do with how nice colimits that happen to be free are. The Cauchy completion of a category is the free cocompletion under splitting idempotents, which I'll just say as words for now. I'd like to explain this one completely, but I'm a little bit unsure still about the timing. That's a fun example because it's a free cocompletion that's also the only possible cocompletion. There's something special about splitting idempotents that there's really only one way to do it. Whereas usually there could be many different like D's here that just add some kind of coproducts or something to C. The incompletion is the closure under filtered colimits, which is something that you might or might not like, but if you're from like pure math, then that's something that sort of Grothendieck algebraic geometry does a lot with. And relatedly, saying almost the same thing, and maybe this will be a little bit more concrete, the category of models of an algebraic theory is a certain free cocompletion of its category of finitely generated free models. Under sifted colimits, if you like, which I don't, which it would probably be off the trail to define, but maybe you've heard that word. Sifted is like a little bit bigger than filtered. So what do these things sort of like mean? What is the vibe of these statements? If you want to understand the whole category of groups, you understand finitely generated free groups really well, and then there's some formal, purely abstract nonsense category theoretic process that tells you everything else that can possibly be true about groups, at least in some sense. In other senses, okay, maybe this doesn't give you the classification of simple groups as formal nonsense, but in some sense. Yeah. That this says that in some sense, everything about the category of groups is contained in the category of finitely generated free groups, and then all the other stuff that seems to be this bewildering and beautiful complexity of everything about groups is actually coming from a very general formal categorical crank where you're just like, just add the sifted colimits.
In the same way that like poly seems like this amazing, wonderful place, but like really set up.
Yeah, it's somehow all of the magic of poly is produced by a general formal crank out of just set up, and then even more in 1 second. Yeah, Dana?
In groups, I seem to remember that free product is a coproduct.
That's true.
Yeah. So the groups, what you were just pointing out there, how does that compare?
How does the free coproduct completion compare, or are you asking about how coproduct completions of finitely generated groups, or so coproducts don't live in these sifted colimits? This is just like basically just directed colimits of subgroups and then certain nice quotients, so the quotients of presentations, reflexive coequalizers. Yeah, thanks. Let me, to finish this list, just mysteriously say sheaves. Kind of. There's more words to fully get that, but you can make me say more about sheaves if you want. And finally, the one that we're actually most interested in today, there is a free cocompletion of any category. Not necessary to say any size constraints here, depending on your foundations, under all small colimits. I think I'm mostly just going to call that C bar as we're working with it in more detail, so I won't. Okay, I will give it a name because I'm about to write one example. Let's just call it colim of C. And so just one, this is probably not spoiling the answer for too many people if I mention that it's well known that set is the free colimit completion of a point. So for instance, poly is the free cocompletion under coproducts of the opposite of the free cocompletion under colimits of a point. So everything in poly is general formal categorical cranks. You add some colimits, and then you flip around, and then you add some coproducts, and it's all produced by completely formal manipulations of a point, which is, so pretty cool cranks. Okay. Yes?
Is there a reason to emphasize that set is the free colimit completion versus the free coproduct completion of the point? Does it matter which perspective you take?
I guess just because I'm going to talk about general colimit completions now. Yeah, so there's this weird coincidence that set is both the free coproduct completion and the free colimit completion of a point, but usually those won't be the same thing.
Right. Yeah. Okay. I'm just wondering whether,
Yeah, and for the purposes of probably not. Like Nelson and co-authors have this paper about free coproduct completions of free product completions. Like, you can definitely also think about it in those terms. Other questions up to there? Okay, I think my strategy will be to try to actually tell you how idempotent completion works, and then to tell you in less detail how the general free cocompletion works. I think that'll be less boring and mysterious, and like those who are going to be on board with the more general thing will be more likely to be with me anyway. Okay, so an idempotent is an endomorphism which squares to itself. So imagine a punctured Euclidean space okay, I'm using x in two pretty different ways there. And so there's this idempotent where you divide by the length of a non-zero vector. If you divide by the length twice, you haven't changed anything. Splitting an idempotent is taking the colimit. Of that diagram. Okay, so what does that mean? It means I need a cocone under that diagram that will also be universal. What's a cocone? I have a map from x to some y, which I'll call R. And to be a cocone, I need E then R to be R again. So a map that stabilizes that idempotent. And to be universal, with that property, there's a particularly good application of the universal property in this case, which gives you everything for idempotent splittings. Because there's another there's a very nice cocone under this diagram. This is a good moment to breathe. Can anybody name a great cocone under that diagram that I already have without saying anything about why? Because maybe that idempotent splitting doesn't even exist, but just within C. Yeah.
Is it just E over X itself?
Yeah, nice. E is a cocone under this diagram because E of E is E. So that's so X itself is always is trying to be the colimit, but probably isn't. So by the universal property, I always, if there is a colimit, if there is an idempotent splitting, then there's also a universal map back to X. I know ER equals R. I know RS equals E. And you can check that R is epi and that this implies that SR is the identity of Y. So that's the reason for the terminology idempotent splitting. Because an idempotent splitting gives R is an actual split epimorphism with S, a split monomorphism splitting it. It just means that. So anytime you have this equation in a category where some map has a left inverse, the left, now I'm having big left and right problems. When anytime you have this equation with diagrammatic composition, this guy is a monomorphism. And that guy is an epimorphism. I always have trouble with left inverse and right inverse anyway. So, and it's like the nicest possible kind of epi and mono because you can see that if I apply a functor to this equation, I get a morphism in the codomain of the functor satisfying the same equation. So split monos and epis are the only kind of monos and epis that are guaranteed to preserve by any functor whatsoever. So they're very special, important kinds of maps. In some sense, they're the only interesting examples in a one category of like stuff that's preserved by any functor whatsoever. That was something vague. I really mean something about absolute colimits, which I could explain less vaguely if someone wants. Yes.
Can you say a sentence?
Yeah. F is a split mono in a category. If there exists G with F, then G, the identity of A.
So here, S is a split mono.
S is a split mono, and R is a split epi. Yeah, and you can say that together they form a splitting of the idempotent E. You split it into its two pieces. S is for section, R is for retraction, if those geometric terms are heuristic for you. Okay, so that's an idempotent splitting. Yes?
Can I tell you what the splitting of?
That's exactly what I was just thinking. I should ask a question. Sophie wants to tell me. Yeah, what is it?
It's the circle.
In R2.
Oh, yeah.
Yeah, if you imagine what's, maybe I'm just in the category of like open sets in Euclidean space. I can still name this idempotent. But what should the splitting be? It should be the universal map out of Rn minus 0 that stabilizes that, or it should be an epimorphism out of Rn minus 0 that you can get a mono back out. And so if you squint at that a little bit, you may convince yourself that the splitting of this idempotent in any category where it exists, and in any reasonable choice of category, it's going to be the n minus 1 sphere. Does that seem at least intuitively plausible to people if the picture didn't come to mind? It's in categories that are sufficiently set theoretic, the splitting of the idempotent is just the image of the idempotent. Right? All of the vectors of length 1. It's the sphere. So let me try in about 3 or 4 minutes to construct the idempotent splitting of a category. Because that doesn't have to exist in Y, right? I could have given that example again in like, yeah, in the category of all open subsets of Euclidean spaces and smooth maps, something like that. So maybe I want to make it split because I think the sphere is cool for some reason, like living on one. And so I want to construct a new category as in this generality that I just erased and probably could have reused. I want to extend C to something where idempotent split. So every idempotent in C is going to have a splitting now, which I'll write I'll just name using E in C bar. Sorry? I of X and I of E. So I've got I, yeah. So if I take an idempotent in C and move it into C bar, now there should be a splitting. And I'm just going to label it with E because I don't know very many symbols. So what should C bar from E to E prime be? Well, imagine that I've given this whole splitting situation for both of these idempotents with Y that I showed over there. So I'm basically thinking about what should a map between Y and Y prime be? And when I say what I want to be, what's going to be a satisfactory answer to this? I'd like to describe what these maps should be just in terms of X, just in terms of C, because I'm making these up out of thin air. So I don't have my hands on them yet. So if I had Y and Y prime, I could produce a map from X to X prime, R, then F, then S prime. And from R of S of S prime, I can reproduce F as S, then R, then F, then R prime, then S prime. There's enough information in maps from X to X prime to reconstruct the maps Y to Y prime. So I just need to know which maps from X to X prime should be basically maps Y to Y prime. So like, what would you need to know maybe about a map from Rn minus 0 to Rn minus 0 to know that like it really wanted to be a map of spheres? This could be a real question, maybe, but it might be a little bit hard. And just in terms of E, I guess this is, can I say which maps on the punctured Euclidean space are induced in this way by a map of spheres without actually talking about the sphere?
You see how it interacts with R and S?
But I don't have R and S yet, right? So I'm imagining.
Sorry, with E, I meant.
Yeah. I should say something about how it relates with E and E prime, right? Because that's all I have. Yeah.
Then your map, then E prime is.
Yeah. What happens if I do E and then my map? E then RFS prime equals RS S prime. Oh, and S and then R was the identity on Y I hopefully still have written over there. If I do E and then my map, nothing happens. And also the same on the other side, RFS prime E prime equals RFS prime in the same way. And you can check that a map X to X prime is of this form if and only if these two properties hold. So we define, and here's the final definition, define C bar E to E prime to be the maps X to X prime, don't say F again, such that E then G equals G and G then E prime equals G. So what's that saying in the geometry? It's saying that you have a map on these punctured Euclidean spaces that doesn't care how big a vector is, right? It just, if you crush a vector to the sphere, you end up in the same place, right? It's constant on the fibers of the idempotent. And it's pretty easy to see that that gives a category, because like I've just like taken it's a subcategory almost of, well, there's a faithful functor into C. And slightly less easy, but not all that hard to check that that is a free cocompletion, that it has the universal property it should.
You only said the onsets for C bar of these things you've introduced, but what about E to Z, some other object?
Right, so these are the only objects I've named.
The identity.
Well, the identity is an idempotent. Yeah.
We have a full copy of C.
Yeah. Oh, okay. Yeah. So right. So I can identify I of C as the colimit of the identity of C, which is an idempotent, and the colimit of an identity is going to be the thing again. So yeah. That gets me. I've covered everything. There's another thing you should also complain about that I haven't checked, that C bar actually has splittings of all idempotents, but I'll leave that for now. Other question or comment?
Are you supposed to say how this is kind of a like it is a cocompletion, but like that this is somehow telling us about how a lot of cocompletions could be, or it like what
Yeah.
is this in the story?
Yeah. So what is this in the story? So what we've seen here is a nice concrete case that I can define the maps in the free cocompletion totally in terms of the data that was coming from the base category. And there's a limit colimit formula that I would like to write here, but that's going to be not very clear in this example, I think. But you could, if you thought about it, I haven't even named the category indexing idempotent, so I better not. If you know there's a limit colimit formula, you can say limit over idempotent of colimit over idempotent and get this too. But yeah, that would take 3 minutes to say well in this example. But this is also a good thing to know in its own right. If you know how to, like the idempotent splitting of that category of open sets in Euclidean spaces is the category of manifolds. So you can reproduce all manifolds in this way, which is kind of sweet. So even the idempotent, if C is open subsets of Euclidean space and smooth maps, then we can kind of see from that example some motivation for the claim that the idempotent splitting of open sets in Euclidean space is the category of all smooth manifolds. And open subsets of Euclidean space are like Calc 3, and smooth manifolds are like differential geometry. So wow, again, look at all this magic from these general categorical cranks. So that's like the smallest non-trivial free cocompletion, but it does have many other properties one might observe in more general ones. That was just adjusting the camera, Sophie, not a question or comment. Other questions or comments? Okay, so now the limit colimit formula is in FAM, and
this is the smallest cocompletion.
yeah.
That's why you started with it.
Yes.
Okay.
Yeah. If you're going to add anything, you're probably going to add idempotent splitting.
Coproducts would be a totally different.
Yeah. So there's some. I need to like try to explain what's minimal about the idempotent splitting. Yeah. So what's tiny about idempotent splittings is that because of the fact that they're characterized by these equations, which are preserved by all functors, splittings of idempotents are colimits that are preserved by all functors. And that's very, very rare, right? Most kinds of colimits you can think of are not preserved by all functors. Coproducts, coequalizers are only preserved by some functors. And so it's sort of very cheap to add splittings of idempotents. There's not wiggle room in how you do it. So those are called absolute colimits, and that's an interesting topic too. Okay, so I would really like to say something about FAM, but I think I should not. But I could come back and say something about FAM. And another interesting point about idempotent splittings that I think I won't write up is that some of you might find it an interesting exercise to check that not all of these maps come from the category of diagrams in C. If you look at an idempotent as a diagram indexed by that monoid generated by an idempotent, and you know what the category of diagrams is,
You might wish that
you might think that all the maps should come from that category, which is something that Evan and Owen and some of us have studied some, but you don't get them all. And the functor from diag to the idempotent splitting is neither full nor faithful in general. So, okay, exercise. Which is important for our software design that uses diagrams, because we use diagrams to present things in free cocompletions. And so that might mean that these are clever presentations that are more minimal, or it might mean that we're missing things we want, or it might mean we're writing things down we don't care about. It's something we have to think about. Okay, so let's leave fam and int and make sure I make the point about the small column completion. Okay, so C is a category. Just recycling notation. I want to add all small colimits, all colimits indexed by a small diagram. If there's a diagram in C, then D, then I must have a colimit, which we'll just label with D. Yeah, that's a good. It's not, although that might feel surprising. Yeah, it's. I guess diag is even farther up because it's a lax cocompletion.
Yeah. So maybe this isn't that important.
Maybe the more the example that might be clearer is take the actual free cocompletion. Right. We know there's a functor from diag to the actual free cocompletion by like factoring into a discrete op vibration. Yeah. And that's the functor. And I don't mean all diagrams, so this would be just diagrams indexed by an idempotent.
Oh, okay. Yeah.
Idempotent diagrams, in this case. Yeah. Yeah. Okay, so I'm trying to add a colimit to every diagram, so I'm just going to do that. Great, I did it. All right, now can I define a category that has all these things as objects? What should be the HOMs between two such formal colimits? Okay, so this is.
Are you like not assuming C is small or something?
I think I'm not going to say anything that cares.
An elephant in the room, man. I don't know if you're doing it on purpose.
No, it's not that big of an elephant, honestly.
No, the other elephant. Like, why aren't you saying presheaf?
Oh no, that one I definitely don't want to say.
Okay.
This is I'm constructing the free cocompletion from first principles. Yeah.
Okay.
Okay. So this so I'm trying to define this category. What can these HOMs be? Well, these are supposed to be these colimits. So I always know what the HOMs out of a colimit are. By definition, depending on your notion of definition, those two indexing categories don't need to be the same. Excuse me. By definition, the HOMs out of a colimit are the limit over J of the HOMs.
Sorry, those J's did need to be the same, right? Upstairs you decomposed off.
Yes, those did. I just didn't name D prime yet. Thanks. D prime takes J prime to C. Thanks. Yeah, now this is the annoying thing where I can't really do diagrammatic composition unless I'm completely unhinged. Okay, so here's already like a very powerful general principle in free cocompletions, is that this is like a representable. D of J is some object in C. And what this is already saying is that HOMs into this formal colimit are going to be characterized totally by their HOMs from these representables. This can be thought of as a diagram indexed by the terminal category, mapping the point to D of J. And those are going to turn out to be a dense generating set for this category. Everything happening in this category of diagrams in C is going to be determined by how it interacts with these singleton diagrams. And that's pretty important. Something very familiar from categories like presheaves and copresheaves, and that happens here too. But now we're in a slightly weirder situation where we need HOMs into a colimit. And in general, there isn't any equality we can write here, right? There's no universal property for HOMs into a colimit. But there is a map in there. So let me try to make this nice and concrete. If I have a map from X to Y, and then I have some colimit of a diagram involving Y, say Y plus the coproduct of some other objects. And this is the component of the cocone for this coproduct in Y. Then I get a map into the colimit, right, by composing with the cocone. For a map into a component of a colimit, I get a map into the colimit. That sounds, I'm saying something that's trivial or obvious or something, but it's very important to have free cocompletions work, because these are the only maps into a colimit that I can name without knowing anything about the category I'm in. These are the only formal maps into a colimit. So there's and the induced map f of I lives in the following colimit. Those maps that are formal aren't all necessarily different from each other. Some can get glued together according to this colimit. But so for every map between objects in the diagram up to the colimiting over the shape of D prime, I get a map into the colimit. I'm just, this notation probably looks pretty heavy, but I'm just doing this to all the different, Y can be any of these D primes of J prime, and I'm taking some colimit over letting them vary. And the big trick of free cocompletions is to say, all right, so the only maps I can think of into a colimit are these ones. The only ones I'm sure have to be there are like, well, I could map into a piece of the colimit and then map that into the whole colimit. What if that were all the maps? can I just set that to be an equality? Again, one can check. I'm sorry, there's a lot of one can checks in this, but there's sort of, yeah. You can check if you're good at, if you know a little bit about colimits, that if you had a co-continuous map out of C bar, then it has to play nicely with this map. So if this is all the maps, then that's going to make this a free co-completion immediately, because all of these maps that factor through the cocone will have to be sent to the corresponding map that factors through the cocone. So if I can make that be an equality, then I'm done, and I can make that be an equality. So what does this look like a little bit more concretely? Let's forget about the limit, because that's sort of the easier part. I do the same thing a bunch of times over different j's. What is the colimit over j prime of C bar from I of something, such as d of j, to I of d prime of j prime? Well, the colimit, is a quotient of the coproduct of all its values. So to get something in this colimit, it's the quotient by some equivalence relation of maps like this, which is just the singleton diagram. Oh, sorry, I'm not even in C bar anymore. This is just C. Now that's annoying now. That's going to be confusing. If I haven't lost people there, which I'm worried I have, I just did some erasures that are using I as fully faithful, which is a cool thing that will turn out to need to be true. Let's just say I'm hoping that maybe I will turn out to be fully faithful, so I can erase those I's. And it will. Sorry about that. But that will make this a much easier picture to draw. OK, what is this colimit? Its elements are equivalence classes of maps like this, modulo the equivalence relation generated by triangles like this. This is just repeating the general definition of colimit in the category of sets, if you know it, right? These are Hom sets, so I'm taking a colimit of sets. And so you can write that as the connected component of the category of all the arrows like this in triangles. And that's possibly comforting, depending on what you're into. What it says is that a map like this comes from choosing a map from C to some object in the image of the diagram D. And then there's some equivalence relation. But so to choose a map between two diagrams, I just choose a map from each one of these guys to one of these guys. And then they satisfy a little consistency, but not as much as you might expect. So the remaining obligation would be to try to get across what this looks like in some concrete examples, and maybe something about why this thing is co-complete. There was a ding, ding, ding. Was that to say, like, try to stop saying new things?
No,
Or?
just to tell you that there's 2 minutes left.
OK, cool. Yeah, so what I think I should do is try to draw some more specific maps between diagrams. Does anybody think I should do something else? Yeah.
You should say something about presheaves.
Let me do that at the end, maybe. Yeah.
I feel like something's missing.
Yeah, I'll say something about presheaves sometime. Yeah. Yeah.
Cocompletions often fully faithful. Right?
They're always fully faithful, and you can sort of the apology for this is that it's not too hard to see that if you can find any co-completion where I is fully faithful, then the free one must be fully faithful. So we're sort of like, this is an ansatz, and it turns out to work. Other comments to there? OK. Right. So what does this look like more concretely? for instance, I could have a diagram like this in C, and I want to map, I'll draw the arrow that like this is a map between these diagrams over there, and then draw its components, and I want a diagram, a map into a diagram like this. This is cool. It's a category of maps between diagrams of different shapes, which is sort of funny, right? There's no hope to talk about natural transformations here. There is this category of diagrams I mentioned there, but these maps are weaker than that. So what do I need to get something in here for these two diagrams, the D and D prime? I need, for every object in the indexing category of D, some equivalence class of maps into the image of D prime. So, okay, so like I have to choose a map from Z to B, maybe, or Z to A, maybe. It's all good, because it's just it's just some map into the image of D prime, and maps Y and X, maybe, into D prime. So call those Fx, Fy, and Fz. So there's some, there's a limit condition and a colimit. The limit condition says these things have to be sort of consistent with each other. So I need names for this, P and Q. And the limit condition says that Fy then P has to be equivalent to, those are bad names, but I can't think of any other letters, has to be equivalent to T then Fz in this category Z down D prime. So that's saying that these choices of components are consistent with composing with T. Right, so the limit says like I've got some family that the elements are sort of equal to each other up to some composition, but the equality is in this connected components thing. Okay, so what does that mean? This means that there's some zigzag between these guys in this category. So I have a map Fz, and I have a map. Oh, these are Y. Sorry. I have a map Fy, then P, and the same would be true for Q. And I have a map T, then Fz. These are maps Y to B, and I need to know that these are connected to each other in the category of maps from Y to the image of D prime. How could I connect these things to each other? I need to get a map in the image of D prime that zigzags these into each other. The only way with this indexing category that I can do that is these things are going to be connected if there exists some map Y to A such that this is such that these triangles commute. If I can choose P or Q in those places, in some way so that there's some map that makes those things commute. So you can see a little bit of a zigzag here, which is characteristic when you're talking connected components. So the takeaway, what is this? So maybe some of you are grokking the whole technical detail of this. Many of you probably aren't. What's the takeaway there? There's some sort of very weak, not all the way natural condition that you can do on maps between these arbitrarily shaped diagrams. It's like some of these triangles like sort of kind of commute, but like only like up to some zigzaggy thing happening in the codomain. So it's this very, very weak notion of map, but somehow it turns out to be enough. Does anyone want to ask anything about that? Yeah? No? You made a motion, yeah? And let me then try and say about 1 to 1.5 more things. One word about how colimits work in there. Let's say why does this have coequalizers? Because that's the hardest kind of colimit. And in particular, let's say, why does this have coequalizers of maps between singleton diagrams? So these sort of representable things. Well, actually, that's kind of too obvious. I sort of already said how to do that. How are there coequalizers between any two diagrams? Okay, so what you do, if you look at what having two maps between these diagrams means, it means you've got a bunch of maps from d of j's to d primes of j primes for some other things. So you build a new category, j double prime, that has j in it, and j prime in it, so start with a disjoint union. And then for every object here, these two maps involve two maps out of that object in C. So I formally add some new arrows in this category I'm building. That's G. And that's it. I stick in some edges that are going to map to the components of F and are going to map to the components of G. And I don't impose any relations on those. And then you can check. Maybe this is just scare quotes at this point. But none of this is you could if you wanted to. That in any category where you have a colimit of D and you have a colimit of D prime, and you have maps between those colimits like this, the coequalizer of those maps will be the same as the colimit of this diagram. So this category has a J double prime has a clear diagram into C, and its colimit is the coequalizer you want. So you can build coequalizers in this category C bar without actually computing any. Yeah, OK, this is getting to David's complaint about presheaves, so let me start a fresh sentence on that if I can. There is another famous picture, as I said at the beginning, of the co-completion of a category, which is that this category I've built here is equivalent in a very non-obvious way to the category of presheaves on C. And so why talk about this C bar at all? Well, it's constructed, I think, in a more elementary follow-your-nose sort of way. There's got to be colimits of every diagram, and then the maps are like the minimal thing they could possibly be. And we didn't really have to know anything about sets except that their limits and colimits exist, maybe, to define this. It's got this stricter universal property. This has the universal property on extending exactly up to uniqueness. And I think most importantly, colimits in C bar are a lot easier to write down on the computer than colimits in presheaves in C. This coequalizer I got just by writing down a diagram with some extra arrows in it, and that's it. That's the coequalizer. Woo, I'm done. To get a coequalizer in presheaves, it's well known the colimits are calculated level-wise. So you have to take a bunch of coequalizers of sets, which basically involves taking the symmetric transitive closure of some relation and then quotienting. And that's a somewhat expensive operation. So this is basically giving you lazy colimits. If you really want to compute how many elements are there in the corresponding presheaf, of course, you have to take that quotient. But this is a very lazy way to just be like, these things are going to get glued together sometime, maybe later. And so I think this is a potentially cool data structure in that sense, and I will stop talking. Thanks. Yeah, it is, how I would usually say it is by factoring a diagram into a final functor followed by a discrete vibration, which you can also describe as taking the left conic extension of the terminal presheaf on J along D, and then that gives you a presheaf on C, and then take the Grothendieck construction. Sophie?
Can you show me why the smallest cocompletion of the one-object category is set?
Yeah. Great question. I was like, what can I illustrate here? I'm a little bored. This is scribble space, right? The small cocompletion of the one-object category, by our definition, is the category of diagrams from a small category to the one-object category. So the objects are basically just small categories. And the HOMs are given by the limit over J of the colimit over K of points, because there's only one map in star. The colimit over a category of a point is semi-famously the connected components of that category. So this means I need to choose a consistent family of connected components of J. I need to choose for every object of J, I need to choose a connected component of K, and that has to be stable under composition in J, which means that since this is just a set, and nothing happens when I compose with something in J, it means I just have to choose the same connected component of K on every connected component of J. And so that's the product over the connected components of J of the connected components of K, which is just that. And so that tells you what this equivalence is in the case of set that I was trying to describe to Brendan in general. In the case of set, the equivalence between star bar and set is take J to its set of connected components.
Can you say anything about which classes of colimits have free cocompletion?
Pretty much everything, unless you're very crazy about small.
Yeah.
Yeah.
So like free cocompletions give you lattice idempotent.
Yeah, KZ monads, yeah.
But I've always wondered if there's some kind of like monadicity theorem you could get for like some more sort of like syntactic description of the colimits wouldn't necessarily give you a.
Yeah, I mean, you can freely co-complete under essentially any kind of colimits you want, and there's a interesting work by Adam Eck and whichever of Adam Eck's friends on sound doctrines of limits. That the like most interesting thing is like if I co-complete under these colimits, have I accidentally co-completed under more, surprise, or not? And they study that pretty thoroughly. Most of the doctrines are like refinements of filtered colimits.
All right, I'd like to give 2 rounds of applauses. First to Kevin for both giving an excellent talk and also doing an excellent job of tracking our attention with questions and pauses. So thank you, Kevin. And of course, the second round of applause goes to the audience for a great job of making sense.